So let's shift gears a little bit now and have a look at the parallels between what we're doing here and this ordinal theory from modern set theory. Okay, so we have to say something a little bit about set theory. And I warn you in advance that if you're a big fan of set theory, you may be dismayed by what I'm going to say here, but it's probably not something new to most of you. Okay, I think that modern set theory is highly problematic logically. That in fact, if you look carefully, it becomes self-evident that this theory does not work. And it's only sustained by our generally universal agreement that we're not going to look at the elephant in the corner. So modern set theory pretends that there is a theory of sets. It's a pretense, without a proper definition of the term set. It does not actually sit down and say what exactly a set is. And this is ultimately the core problem with modern set theory. It really is at this very fundamental level that if you're going to talk about groups, you have to define what a group is. If you're going to talk about fields, you have to say what a field is. If you're going to talk about differentiable manifolds, you have to say what a differentiable manifold is. That's the way mathematics is. It starts with definitions. But set theory does not do that. It tries to avoid defining completely, clearly, and precisely what the fundamental term is. Of course, informally, we have an intuitive understanding because the word set is used in English language. We can look up a thesaurus or a dictionary and find lots of more or less synonymous words. Words like collection, family, bunch, menagerie grouping. I've talked about this before in previous videos. So we have a whole bunch of words at our disposal so that we can at least informally say, well, a set is a collection of such and such, or it's a gathering of such and such, or it's a number of such and such. You know, we can do that. But it's clear that we're just transferring the burden of definition from one word to another. It's not really solving the problem. Okay, so that's informally. So informally we have this intuitive understanding. But formally, modern set theory proceeds by considering set to be an undefined term. So it pretends that, in fact, we don't know what a set is, and we don't need to know. It's an undefined term, which is subject to rules or axioms which replace theorems. So instead of having a proper definition upon which theorems are then created and proven, we've decided to not define what the word set precisely means. And so the various facts about sets, which would ordinarily be theorems if this was any other mathematical subject, are replaced with rules, axioms, things that you believe in because you're told to believe them, or perhaps because you believe that they correspond to your intuition about what ought to be true, assuming that your intuition actually reflects something valid. What's really happened, though people don't want to say it this way, but this is really close to the truth, is that philosophy has come to the rescue of modern mathematical foundations. The mathematicians themselves were not able to create a proper framework for set theory. They tried, but it didn't work. It failed in a very embarrassing and flamboyant way, in fact. And then the philosophers were kind of recruited. They were brought in and they created this essentially philosophical framework. It really is what it is, which is now the underpinnings not of just set theory, but remarkably of supposedly all of pure mathematics. Absolutely incredible state of affairs, people. Absolutely incredible. And future generations are going to shake their heads in disbelief at what we've gotten up to and what we've allowed to pass as a proper foundations for the subject. So why did modern set theory go down this road? Why this retreat from proper definitions? I'm going to be explaining the history of this in some detail this year. We're going to have a very close look at this whole story. We're going to look at the axioms very precisely and carefully and critically, and we're going to unravel the whole logical knot. So it's not just the definition of sets themselves which are missing from the current theory, but pretty well all the other adjacent terms are also sort of imposed without proper definitions, such as, for example, element, union, power set, intersection. Okay. So none of these terms are pinned down precisely. And you might say, well, why did people do this? This is clearly not a very desirable state of affairs, so what motivated mathematicians to accept this? And the simple reason is the following, is that if you accept Cantor's definition, so here is Cantor's original definition of what a set is. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. All right, so if you are going to accept this as a definition of set, then you have serious problems, because this is just not precise enough. What are objects of our perception or of our thought? And you've already seen me give various lists of suitably ambiguous kinds of sets, and do they really deserve to be called sets or don't they? But the fundamental problem is already at this level here, which is really sort of at the level of a 10-year-old objection. Right? If you're going to just allow yourself to think up sets, like I'm thinking of certain things, the set of all fish called Fred, okay, that's a set because I'm thinking of it. The set of all happy thoughts, yes, that's a set because it's something that I'm thinking about. So if we play this game, then even primary school children can easily come up with ever more and more outlandish sets. And eventually some kid is going to say, hey, I've got a set that will beat everybody else's set. How about the set of all sets? Okay, it's not a particularly brilliant insight to suggest that we should consider this, right? If you're going to consider sets of anything, then how about the set of all sets? And this is really the fundamental core problem. It's the fact that you can create a phrase like this to create an object which is almost self-evidently contradictory, or at least highly dubious. Here's a set U, and it's got every single possible set you could possibly imagine. The set of all fish called Fred is in there. The set of all happy thoughts is in there because this contains all possible sets, including U itself, because U is a set, and so it belongs to the set of all sets. Okay, but that means that inside this U, if we look more carefully, there's another U inside this copy of U, and inside that there's another copy of U. And in fact, this U is sitting inside some bigger thing, which is also U, and so this is infinite digress in both directions. And I think most reasonable people would say, guys, you have crossed the line into nonsense. It doesn't work. This is silly. You're obviously going to be faced with self-referential problems here. Okay? So people generally think that it's because of Bertrand Russell's paradox that set theory collapsed, but in fact it's really just the ambiguity in the definition of Cantor, that even at this level here, which is, I think, essentially like a 10-year-old kind of idea, you can see that this is not really going to work. Right. There's something seriously logically problematic with trying to conjure up set theory when you're only going to have something that's so vague like this as your fundamental definition. Okay, so I realize that people are going to kick and scream about this. Analysts are going to be loath to accept this because they all know that modern analysis is built on a foundation of set theory. That's the ultimate justification for our model of the continuum as real numbers. And without real numbers, most of modern analysis is very seriously weakened. So there's going to be strong resistance to actually even addressing this entire issue. Most analysts would just rather not think about the problems with set theory. In fact, most mathematicians would prefer not to think about the problems. But the problems are there, they're very serious, and there is a better way. So we are going to point to a better way. But there's a lot more to be said about that, and I will be talking at length about this entire issue. So now let's go to cardinal and ordinal numbers, which are part of this modern set theory, which we don't believe in. We don't believe in cardinal and ordinal numbers. So neither of these are proper mathematical theories, in my view. But nevertheless, let's have a look at the standard story of ordinals in particular. So here's a relatively simple, quick introduction to ordinals, sometimes also called the theory of well-ordered sets. Okay, so I'm going to just show you the standard hierarchy of ordinals. So we start with the empty set. So everything is a set in this theory. That's maybe important to say. So everything we're going to consider from now on is going to be a set when we're regarding ordinals. And the simplest possible set is the empty set. Fair enough. And that's going to be given a name. We're going to call that 0. That's going to be our representation of 0. And that's certainly not unreasonable. I perfectly buy that. And then we have to build up numbers from that. And the idea is to build up numbers by just looking at sets of sets, possibly of sets, and so on. So the simplest set that we can build from the empty set is a single set whose sole element is the empty set. So it's the set consisting of 0. And let me note that the set consisting of 0, which is this thing here, can also be written as O union this set, because O is the empty set, and empty set union anything is just this thing here. All right, now the number 2 is defined to be 1 union the set 1. So it's a new set, which is a union of 2 existing sets. The first set is the set, which is 1, and then the next set is the set which contains 1. So here's this union. So it's a big set, and it's got one element there, which is the element from 1, and then the other element here is actually this entire set. So this is the union of the set 1 and the set consisting of 1 as a sole element. Please check to see that you agree with that. And then 3 is defined as 2 union the set 2. So 2 is a set, namely it's this set right here. And then we take the union of that set with the set consisting of just the element 2. All right, and here you see all of this put together. So we're taking the union of this, which is that part there, together with the set 2. And there's the set 2. Okay, notice that I'm reverting to standard notation here for sets, so I'm using commas because this is traditional treatment. So a standard set theorist would look at this and say, yes, this is the usual way that we build up natural numbers from sets, essentially from just the empty set and constructions with sets. So all of these sets that we've constructed so far, 0, 1, 2, 3, and so on, they are all called ordinals. And the pattern that we've used to go from 0 to 1, and then from 1 to 2, and from 2 to 3, and so on, can be generalized to define the successor of any ordinal. So if alpha is any ordinal, then its successor alpha prime, which we can also write as alpha plus 1, is defined by, well, here's that rule that we've seen. Alpha prime is the union of the ordinal alpha together with the set consisting of one element, that element being alpha. All right, so this is a set, that's a set. We're taking the union of those to create another ordinal, which is the successor of whatever ordinal alpha we started with. Okay, so this is actually then a perfectly logical, if complicated, way of constructing the natural numbers using only finite set theory. I have no objections with this as a framework for natural numbers. I think it's not the most efficient way. I think that it's definitely constrained by having this idea that sets are the right data structures to use. We know that there are these other data structures that are around, namely lists and ordered sets, and in particular multi-sets, in addition to sets. And having these 4 different types of data structures around provides us with more flexibility. So we are going to, in fact, be looking at something like this, but we're going to be doing it in a different way because we're not constrained to just stick with sets. But if you were constrained to stick with sets, then this would be a perfectly natural, in fact, reasonable and somewhat clever way of creating natural numbers from set theory. And this is, I think, basically attributed to John von Neumann, a brilliant American mathematician of the 20th century. Okay, so we have now a way of constructing natural numbers, including 0. So 0, 1, 2, 3, so on. They're all sets. They're all things we call ordinals. And, okay, we have a sort of inductive way of getting from one to the next one. So far, so good. All right, so now for the dubious part of the construction of ordinals. The idea of taking limits of ordinals. So suppose we have alpha 1, alpha 2, alpha 3, and so on, a sequence of ordinals. So we have some rule that generates what we consider a nice sequence of ordinals, or a suitable sequence. Okay. Then their limit is defined to be their union. Alpha 1, union alpha 2, union alpha 3, union alpha 4, and so on. We could call that alpha infinity. So this is a way of starting with a sequence of ordinals and taking some limit of that sequence. And it's analogous to the kind of limit that we were using in our construction of operations. But it's quite different. So for example, if we consider the sequence 0, 1, 2, 3, sort of the fundamental sequence of natural numbers themselves, or just our basic ordinals, then we get the limit ordinal. Right? So each of these are sets. In fact, each is a subset of the next one. So when we take the limit, we get the set 0, comma 1, comma 2, comma 3, and so on. What we're getting when we take the union of all of these things is an infinite set. And here's where the problem really arises. All right? The problem is that if there's an infinite number of elements in your sequence, then you're asking to take a union of those infinite number of sets, and that's simply something that you cannot do. That's the basic problem. You cannot do that. You can take the union between 2 sets. And then if you repeat that, you can take the union of 3 sets. You repeat that, you can take the union of 4 sets. Fine. But you cannot take the union of an infinite number of sets. It's not actually even defined. So I hope we can appreciate the difficulties here, because these 3 little dots, which represent the union, all the other natural numbers, we know that this is hugely problematic, because we have now some experience with numbers which are considerably bigger than just 1, 2, 3. We know that this seemingly simple-minded pattern, one number followed by the next, doesn't in fact really represent what's going on here. Along the way here are things like z, and then z prime, and then like that number 3 star n4 that we started to write down an expression for. And in between 0, 1, 2, 3 and z prime and this big number are untold numbers which cannot be written down in our universe because they are too big. These are numbers whose existence is problematic. And that's not to speak of at all the numbers, supposedly, which are beyond even that biggest number that we contemplated. And even numbers which are so big that you cannot write down any expression for them at all in the universe. So eventually, the universe is only so big, eventually you just run out of possible numbers that you can write down in the universe. It's only a finite number. We don't know how many, but there's an upper bound. Okay? But we're pretending that none of that applies here, that we're just closing our eyes to the reality of mathematics as it really is, and pretending that this little sequence keeps on going in its simple-minded fashion, and that therefore we have all of the natural numbers in one big set, and that's going to be a new object which we're going to call the ordinal omega. That's the heart of the problem right there. The heart of the problem is already at omega. This object does not make sense. Simple as that. But the set theorists pretend that it does, because it sort of coincides with Cantor's vague prescription. Well, we can think about all the natural numbers, and because we can think about them, we can put them all in a box. Okay, so now the idea is that using successors and limits, set theorists now construct a hierarchy of ordinals. So this is just the beginning, and now by combining these two operations, we can build higher and higher and bigger ordinals, which, somewhat surprisingly, has a remarkable similarity to our hierarchy of arithmetical operations, the star lambdas. Even though these are quite different objects, and even though this is, in my view, highly dubious logically, nevertheless, there's a very close parallel to what's going on. So, for example, once we have omega, we can talk about omega plus 1, which is the successor of omega. And by definition, that's the set omega union the set omega. Okay, well, what does that look like? Well, here is the union. So there's omega, and there is that set containing omega, and we've taken the union. Or we could sometimes write it like this. So here's sequence 0, 1, 2, ... representing all the natural numbers there. And then there's a little colon with an omega afterwards, representing the fact that after you've put in all the natural numbers, you finish that task, closed off the sequence with a little semicolon, and then you add omega itself. Omega then being the same kind of big thing. All right, so that's the successor of omega. And then we can take omega plus 2, which is the successor of omega plus 1, which is omega plus 1 union the set omega plus 1. And we get something that looks like this. And we can carry on, and then once we have these guys here, then there's a limit procedure that we can take, and then we can take the union, and we'll get 2 omega, which looks like this. Then it has a infinite sequence of the sort of first level ordinals, just natural numbers, and then these sort of second level fellows, omega, omega plus 1, omega plus 2, etc. And there's another infinite sequence of those. Okay, so then the story continues, and it's very parallel to the kind of picture that we were drawing, except that the crucial role of limit has changed dramatically. The objects that we're considering are quite different. We're talking about infinite sets here, whereas we were talking about operations between natural numbers, right? And here this limiting operation involves doing an infinite number of things. For us, that's not the case. For us, the limiting operation involves writing down a formula that allows us to compute very concretely and specifically, if in a very complicated way, the product of two natural numbers. So the limit of omega, 2 omega, 3 omega, and so on ends up being omega squared, and then the limit of omega, omega squared, omega cubed is omega to the omega, and we get a hierarchy of ordinals this way. In fact, the hierarchy extends much further depending on various sort of higher constructions that you impose as you go on. So we see there's a correspondence between what we're calling n and what the modern set theorists call omega. So even though they are very different, the contexts are very different, still there's a correspondence between these two kinds of ladders, suggesting that the ladder itself is of some kind of independent interest and has a life of its own, perhaps independent of ordinals and maybe independent of operations as well. And I think that is the case. It's a very interesting object. And next time I think we want to explore a little bit more of it. So please try to get your head around what we've done today with regard to these higher arithmetical operations. And we're going to push further, and you're going to see how these different levels of limits start playing an important role in determining what kinds of sequences are suitable for taking further limits. It becomes quite interesting and sort of self-referential in an interesting way as well. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.